Welcome to AP Calculus. This is the first set of videos we'll be doing, learning about Unit 1, Limits, Continuity, and the Squeeze Theorem. Alright, let's take a look at Section 1.5, Infinite Limits, Limits at Infinity, and Asymptotes. We're going to use our calculator to fill in this chart, but before we do that, let's take a look at what's happening here. We have the limit as x goes to 0 of 1 over x squared. That's going to equal infinity because each side of the limit equals infinity. Let me prove that to you in two different ways. The first way will be this chart. So go ahead and take a minute and fill the chart in. There's a lot of ways you can do that using your graphing calculator or using a calculator on your iPad. Let's walk through how to do it on your graphing calculator. The best way I would do it is to enter it into the y equals. I would enter 1 over x squared. And then I would hit the trace button on my graph and enter each one of these values in. You can also make a chart, that's another way, or you can repeatedly type it out into the main screen. There are a lot of ways to do this. So have a couple minutes and please fill in this chart. So hopefully you did that, and you can see from the left, as we get close to 0, it looks like we're approaching positive infinity. And from the right, as you get close to 0, it looks like we're approaching positive infinity. So our limit approaches positive infinity. We can also see this on the graph. We do a graph of 1 over x squared. As we get really close to 0 on the left, it goes all the way to infinity. And as we get really close to 0 from the right, we go all the way to infinity. Now, of course, infinity is not a number, so we kind of fudge and say it gets close to infinity or it approaches infinity. We often say it is infinity, even though, of course, we can't equal infinity, and equaling infinity is not equaling a number. But for shorthand, it kind of simplifies what we talk about, so we often say it. Now we have a very similar example. We're going to take a look at the limit as x goes to 0 of 1 over x. We're going to look at the left-hand limit and the right-hand limit. So please take a minute and fill in this chart. So hopefully you got similar numbers to me when I filled in the chart. And you can see that as we approach 0 from the left, we're going towards negative infinity. And as we approach 0 from the right, we're going towards positive infinity. Since these are not approaching the same infinity or the same number, we would say the limit does not exist for these. And let's see that on the graph as well. As I approach 0 from the left, you can see I shoot down to negative infinity, and as I approach it from the right, you can see I shoot up to positive infinity. In example 2, we're going to look at the limit as x goes to 0 from the right of natural log of x. So we're going to do the same chart method, and then we're also going to look at the graph. So take a minute, please, and do the chart. So hopefully you got similar numbers, and you're able to see that the natural log is growing unboundedly as we get close to 0 from the right. So we're going to say it approaches infinity. And we can see that from the graph as well. Oops, negative infinity. And we can see that from the graph as well. As we get close to 0 from the right, we shoot all the way down to negative infinity. So to solve these limits, we're going to take the same approach that we usually do. We're going to look at the limit as x goes to 3 from the right of the numerator, and the limit as x goes to 3 from the right of the denominator. So for the numerator, I'm going to have 2 times 3 plus 1, or 7. For the denominator, we're going to have 3 minus 3, or 0. And now, well, I know that's not allowed. I can't have my denominator equaling 0. What I can do is think about what's going to happen here. If my numerator approaches a fixed number, and my denominator gets smaller and smaller and smaller. So what that means is it's getting arbitrarily close to 0, or really, really close to 0. Well, what's happening is that this whole fraction is going to approach infinity. So if I keep dividing by a smaller and smaller number, it's like multiplying the numerator by the reciprocal of that division. So if I divide by 0.1, that's like multiplying by 10. I divide by 0.01, it's multiplying by 100. I divide by 0.001, multiplying by 10,000. And all those, and so on and so on. Therefore, the numerator is going to grow and grow and grow, and the whole function will grow. So my overall limit will approach positive infinity. Let's do the same thing for the next problem. Same idea, we're going to break it up into the limit as x goes to 1 from the left of x squared, and the limit as x goes to 1 from the left of ln x. So the limit as x goes to 1 of x squared is just going to be 1 squared or 1, and the limit as x goes to 1 of ln x becomes ln of 1, which is 0. And again, we're not allowed to do that, so we need to think about what else we can do. So we're looking at the left-handed limit of this. And the denominator is getting closer and closer to 0. But what's happening here is that I know that the limit is less than, the natural log of x is less than 0. So we're getting closer and closer to 0 in the negative direction. So it's going to be 1 over a negative, which will bring me to negative infinity. As I said, these problems are worked out on page 130, so I suggest that you go back and reread some of that as well. Here's a summary slide on 1.5 of everything we just discussed. I'm going to let you have a minute to absorb all of this. This again can be found on page 130. Now let's talk about vertical asymptotes. An asymptote is where a function comes really close to a number, but it doesn't actually hit that number. It just approaches it. We saw that on the previous slide when we approached infinity. And here are some conditions where the line x equals c is a vertical asymptote if any of the following pieces are true. I'll give you a second to read through that. And when we think about where a vertical asymptote could be, we're looking at example 4 on page 131. We're looking at the number that is not part of the domain. So when I look at this, I have x over x minus 3 squared. I know my denominator cannot equal 0, so I know that x cannot be 3. So 3 is going to be the number that might be a suspect for having an asymptote there. So let's pick numbers on either side of 3. So we can pick like 2.9, 2.99, and 2.999, and then 3.001, 3.01, and 3.1. So take a second, please, and fill those numbers in using your calculator. Hopefully when you filled in your chart, you were able to come up with similar numbers that I did. And you can see that as we get close to 3 from both the left and the right, we're growing unboundedly, or we're approaching infinity, which means, yes, we have a vertical asymptote at 3. Here's a summary slide of the different properties of the limits at infinity. This can be found on page 132, but I've copied it over here so that you can get it into your notebook. We're at a very exciting point here on example 8 from section 1.5. We're looking at the limit as x approaches infinity. This also holds true for x approaches negative infinity. Actually, this one's supposed to be a negative infinity. And it's a really cool concept that we're going to talk about. So in number A, or part A, the limit is x goes to infinity 3x squared minus 2x plus 8 over x squared plus 1. So I want you to imagine that you have $1 million. Do you care if you add $8 or add $1 to your $1 million? I mean, since we don't have $1 million, yes, we care a lot, but if you were like Bill Gates, $8 or $1 definitely doesn't matter to you. So we're going to ignore those. And now we have the limit as x goes to infinity of 3x squared minus 2x over x squared. Again, we're thinking about if you have $1 million. If you have $1 million squared, that's a lot of money. If you take away 2 million, do you think you'll notice? Hopefully. Again, I would notice losing $2 million because I don't have $2 million. But if you had $1 million squared times 3, you're not going to notice the 2 million that's gone. This only happens when x goes to infinity. That's the only time I get to do this. Again, I get to reduce this problem to the limit as x goes to infinity of 3x squared over x squared. Now if we have a million squared over a million squared, those will cancel out as well. And the limit as this function goes to infinity is just 3. Now this might seem like a difficult concept, but I think it will make more sense as we keep going. In this case, you have the limit as x goes to negative infinity of 4x squared minus 5x all over x cubed plus 1. So again, I want you to take your idea of $1 million, and this time it's a negative million. So you have negative $1 million. You owe someone $1 million. Do you think it matters if you pay back $1? Probably not. For that matter, do you think it matters if you pay back 5 million if you owe 4 times a million squared? Probably not. So this problem is going to reduce to limit as x goes to negative infinity 4x squared over x cubed. And again, we can reduce that again. We have the x squared and the x cubed on the denominator. So 2 come out of there and we're left with just the 1. So we get the limit as x goes to negative infinity of 4 over x. So now let's think about this problem. You have $4 and 1 million people that you need to spread that $4 amongst. How much money is every person going to get? Hopefully you said nothing, or really close to nothing. They're going to get some cents, a fraction of a cent, but it's going to be pretty close to nothing. That's because this limit is 0. Now let's take a look at when the numerator is higher than the denominator. So again, because we're going to infinity, this is the only time we have the privilege of doing this. We cancel off everything that's not the highest exponent. So we have the limit as x goes to infinity of 5x to the 4th over 2x squared. And I can reduce this to the limit as x goes to infinity of 5x squared over 2. So now I have 5 times 1 million squared, and I split it amongst 2 people. Well, we're each getting a lot of money. So this, as the $1 million grows, this is going to go to infinity. So let's take a look back and make a summary of what we've just done. So for the summary of what we've just done, this, again, I'm going to repeat myself over and over. This only matters when we go to infinity. If we're going to infinity and the power in the numerator is larger, then we go to infinity. Our limit approaches infinity. Or negative infinity. It kind of depends on what's happening. If we're squaring it, it's always going to go to positive. You know, such numbers still follow their usual paths. If our power in the denominator is larger, then we're going to go to 0. And if the powers are the same, then it's going to be the constants of the highest power. This comes in really useful when we're trying to do limits quickly to infinity. Of course, there are other ways to do limits, but those take a lot longer. Let's talk about horizontal asymptotes now. In order to find the horizontal asymptotes, we take the function as it goes to negative infinity, the limit of the function as it goes to negative infinity, and the limit of the function as it goes to positive infinity. And the lines that it approaches, y equals L and y equals M, those would be our horizontal asymptotes. Let's do an example of that with the horizontal asymptote. In example 11 on page 138, we're going to find the horizontal asymptote, if there is any, of the function 3x minus 2 over 4x minus 1. So we'll take the limit as x goes to negative infinity of the function. And since we just learned our excellent new trick about taking the limit as x goes to infinity, we can use that now. We'll reduce or cancel everything that's not so important to us right now. So the 2 and the 1, and we just get 3x over 4x, which will just get 3/4. So our limit as x goes to negative infinity is 3/4. That means we have a horizontal asymptote at y equals 3/4. We're going to do the same thing going to positive infinity. And in this case, we're going to see that it doesn't make a difference if we're going to positive infinity or to negative infinity. We're still going to get 3/4. So of course we don't need to write it twice, just our horizontal asymptote is y equals 3/4. It does occasionally matter, depending on the function, when you go to positive infinity or negative infinity. So it's important to take a break and make sure that you do both sides to examine what your horizontal asymptotes will be.